This video is going to cover the last section in chapter 2, which is 2.6, and it's finding a function's domain. So we've already talked about domain in previous sections, and that's the set of all the possible x values that pertain to the function. So a function's domain is the largest set of real numbers for which the value of f of x is a real number. So in other words, if we think of the function or the equation as a machine, if I input a value of x, the machine should spit out a real value of y, right? But if I input a value of x into the equation and it's not able to spit out a real number, if it produces something that's undefined, then that value of x has to be excluded from the domain. It's not part of the domain. So think about it that way. So for example, look at A. I have f of x, which is the same thing as y, right? Y is equal to 2x plus 5. Is there any value of x that when I input it into this equation, it's not going to produce a real value for y, or it's going to break the machine? So whatever I input for x, we multiply it by 2 and then add 5, right? And that gives us y. Do we need to exclude any numbers from this domain? That's how you have to think about it. Are there any numbers that need to be excluded? Is there any values of x? Are there any values of x that I can't plug into this equation? And in this case, there's not. X could be any real number. I could multiply any number by 2 and add 5. I'll always get a real number for y. And this is also a linear equation. And remember, the domain of a linear equation is all real numbers. So the domain in this case is going to be all real numbers. So negative infinity to positive infinity. Or we could use set builder notation and we could write all values of x such that x is real. It's a real number. Look at B. We have y equals x squared plus 3. And we can picture what this function looks like now, because in the previous section, we looked at transformations, right? This is our squaring function, which is a quadratic, right? It's a parabola that goes through the origin, but we're going to shift it up 3 units. But remember the domain of x squared, it's all real numbers, right? I could input whatever I want for x and square it, and then add 3. I'm always going to get a real number for y. So the domain is going to be all real numbers or all values of x such that x is real. But now let's look at C. We have a fraction, 3 divided by x minus 4, and we have x is part of the denominator, right? We have this expression x minus 4. Ask yourself, can x be anything? Can I plug anything I want in for x? Well, you have to be careful because we can't divide by 0. The numerator is 3, right? And suppose the denominator was equal to 0. So what if we had 3, but we tried to divide by 0? That's a problem. That's not defined. That's not a real number. So it's going to break the machine. So if I tried to plug in a number for x, but it was going to produce a 0 in the denominator, we have to exclude that value from the domain. So the trick is, whenever you have a fraction and you're trying to figure out what to exclude from the domain, take the denominator, in this case x minus 4, and set it equal to 0, because whatever is going to make x minus 4 equal to 0, we have to exclude that value of x. So solve this. So set the denominator equal to 0 and solve. So if I add 4 to both sides, I'm going to get x is equal to 4. So look, if we go to plug 4 in for x, we're going to get 4 minus 4, which is 0, right? We'd end up with 3 divided by 0, and that's a problem. We can't divide by 0. So x is not allowed to be equal to 4. We have to exclude this value from the domain. Let me just rewrite that. So my domain is going to be all values of x such that x is not equal to 4. But it could be any other number. We're allowed to divide by a negative, a positive, a fraction. We could divide another fraction by a fraction, right? Remember complex fractions, we just can't divide by 0. So whatever is going to make that denominator equal to 0, whatever value of x, we have to exclude it from the domain. We could write it in interval notation also. So it would be every number from negative infinity to 4, but not including 4, union 4 to infinity, again, not including 4. So that would be every number from negative infinity to positive infinity, but not including 4. So D is very similar. We have 5 divided by 2x plus 3. We have another fraction. So the denominator can't equal 0. Whatever 2x plus 3 is, we need to figure out when it would be equal to 0. And let me just kind of separate these questions so we could see them better. Okay, so when is 2x plus 3 going to equal 0? 2x plus 3 is going to equal 0 when x is equal to, so let's solve this, right? So we're going to subtract 3 from both sides. And we're going to get 2x equals negative 3 and then divide by 2, right? So we're going to get x equals negative 3 halves. So when x is equal to negative 3 halves, the denominator of this expression would be equal to 0 because it's 2x plus 3, right? But 2 times negative 3 halves is negative 3, and negative 3 plus 3 is 0. So we have to exclude this value from the domain. So my domain is going to be all values of x such that x is not equal to negative 3 halves. It could be any other real number except for negative 3 halves. The other thing that you have to look out for, the other type of expression when we're trying to figure out algebraically what the domain of a function is square root symbols, right? Because we have restrictions when we take the square root. We can't take the square root of a negative number, right? That's not going to be a real answer. So look at E. We have the square root of x plus 4. We have to think about what would make x plus 4 negative. So in other words, we have to set x plus 4 greater than or equal to 0. Because we can take the square root of 0, it's just 0. And we could take the square root of any number that's greater than 0, because all numbers greater than 0 are positive. We just can't take the square root of a negative number. So we have to make sure that whatever's underneath the radical has to stay greater than or equal to 0. So we need to take x plus 4 and set it greater than or equal to 0. And now solve. So if we subtract 4 from both sides, we're going to have x is greater than or equal to negative 4. . So So let's rationalize that, right? Let's use -4 because x, we're saying that x could be greater than or equal to -4. If we were to plug -4 in for x, we would have -4 plus 4, which is 0. And the square root of 0 is 0. Pick another number that satisfies x being greater than or equal to -4. What about -3? If we were to plug -3 in for x, we would get -3 plus 4, which is 1. We could take the square root of 1. So as long as we pick numbers that are greater than or equal to -4, we won't end up with a negative number underneath the radical. So my domain is going to be all values of x such that x is greater than or equal to -4. Or in interval notation, we could say that x goes from -4 to infinity. So f is going to be very similar. We have the square root of 3x plus 6, and we want to figure out what the domain is of this function. And again, we can't take the square root of a negative value. So we have to make sure that whatever 3x plus 6 is that it stays greater than or equal to 0. So let's solve for x. So if we subtract 6 from both sides, we're going to get 3x is greater than or equal to -6, and then divide by 3. So we're going to get x is greater than or equal to -2. So let's try -2 because x is allowed to be greater than or equal to -2. So if we plug -2 in for x, we're going to get 3 times -2, which is -6. And -6 plus 6 is 0. Square root of 0 is 0. Let's pick another number that's greater than or equal to -2. How about -1? If I plug in -1 for x, I'm going to get 3 times -1, which is -3. And -3 plus 6 is 3. And I could take the square root of 3. Now I want you to see, let's pick a number that's not greater than or equal to -2. What about -3? If we plug in -3 for x, I'm going to get 3 times -3, which is -9. -9 plus 6 is -3. I can't take the square root of -3, right? We can't take the square root of a negative number. So you see why that doesn't make sense. So my domain has to be all values of x such that x is greater than or equal to -2. Or if I want to write it using interval notation, all values of x from -2 to infinity. And let's do one more just to make sure, we got it. Let's look at G. So what is the domain of the function 1 over x squared minus 49? Well, we have a fraction again. And remember, like parts C and D, when we were working with a fraction, the denominator can't equal 0. So we have to think, okay, when would this denominator, x squared minus 49, be equal to 0? So if we add 49 to each side, so we set the expression equal to 0, right? We're going to get x squared equals 49. And let's use our square root property, which we learned previously, right? Square root of both sides. So that's going to give me x is equal to plus or minus 7, right? We have two roots, positive and -7. So if x is either positive or -7, my denominator is going to be equal to 0, right? Because plug in 7 down here. We're going to get 7 squared minus 49, which is 49 minus 49, and that's 0. We can't divide by 0. What if x was -7? Then I would have -7 squared minus 49. And that's also 49 minus 49, and that would give me 0. So the two numbers that we have to exclude from the domain are +7 and -7. So my domain is going to be all values of x such that x is not equal to -7 or +7. And we could write it like that in set builder notation. So x could be any real number such that x is not equal to -7 or +7. So that's how we find the domain of an equation. So if we're given the equation of a function, I would think along those terms. Anytime we have a fraction, know that the denominator can equal 0. And whenever we're working with the square root function, whatever the radicand is, right, whatever is underneath the radical, that expression also can't be negative. So once we figure out what to exclude from the domain would be everything else, every other real number except for what we're excluding. So this wraps up chapter 2. And in the next lecture, we'll start chapter 3.